All right, so this is part 2 of section 4.4 in concavity. So we just discussed what it means to be concave out, concave down, and what an inflection point is and how to actually find one. So now we're going to do an example that kind of details that out. So let's do this first one. So find all inflection points and discuss the concavity of the function. So we have our function, and since it was involving the second derivative with inflection points, we need to get to the second derivative. So let's start with the first derivative. So negative 3x squared plus 6x. Now we'll just jump right to the second derivative. So negative 6x plus 6. So notice we didn't do anything with the first derivative. We just found it, kept going, and there we go. Because inflection points deal with the second derivative, not the first. So again, it's similar to how we're dealing with critical numbers. It's just now everything's translated to the second derivative. So we're going to set the second derivative equal to 0. And you want to figure out what makes it 0 or undefined. So in this case, pretty easy. X is going to equal 1. So right here is potentially where we've got that inflection point. But in order to have an inflection point, concavity has to switch. So we need to see if the graph is going to be concave up or concave down, which means we got to investigate the sign of the second derivative. If it changes in either direction, positive to negative or negative to positive, then we have an inflection point. But we got to see if there's a sign change. So that's why it's still similar to critical numbers, because you're going to do that number line chart and investigate what happens. So place the values of x that you found on your number line in always in numerical order, and then you're going to choose some test numbers. So anything less than 1, so let's go with 0, and anything bigger than 1, and we can go with 2. And we're going to take these numbers and we're going to plug them into the second derivative so we can figure out the sign of the second derivative. Is it positive or is it negative? So when x is 0, plug it in here, and it comes out as a positive. And when x is 2, plug it back into the second derivative again, and it comes out as a negative. So whenever it's positive, that's where it's concave up, and wherever it's negative, that's where it's concave down. So negative infinity to 1, concave down from 1 to infinity. And since it did switch in sign, it changed from positive to negative, now you know you have an inflection point. So your inflection point, we know that x is 1, so now we got to search for that y coordinate. So when x is 1, plug it back up into the original function to give you that y value. So when x is 1, we're actually going to come out with a y value of 0. So just remember too that these are, when you're talking about the concave up, concave down, these are intervals. An inflection point is an actual point. So this is what we wrote here, the 1, 0. That's not an interval, it's a point. So x is 1, y is 0. All right. Let's go ahead and try example C, just to make it a little bit more of a challenge. So still we need the second derivative. So the first derivative, got to use the quotient rule. So low times the derivative of the high minus the high times the derivative of the low. Square the bottom, and there you go. So we end up with 1 minus ln of x over x squared. So we're not dealing with critical numbers. So go ahead and get your second derivative, and hey, look at that. We got to use the quotient rule again. Okay, so the derivative of the top, negative 1 over x times the bottom, so x squared, minus the derivative of the bottom, so 2x times the top, all over x to the 4th. Okay, so let's just simplify this thing down. So we have a negative x minus 2x plus 2x ln x all over x to the 4th. So if we started to combine like terms, negative 3x plus 2x ln x over x to the 4th. Well, now we've got an x in every single term, so we can simplify it. So negative 3 plus 2 ln x all over x to the 3rd. And this is what we're going to set equal to 0 and figure out what makes the top 0 and what makes the bottom 0, just like you did for critical numbers. So the denominator, that one's easy, it's just 0. The top, you can look at it on its own. If you can't do it in your head, so to set the numerator equal to 0, we can move the 3 over, divide both sides by 2, and then what gets rid of an ln? An e. So we have the fun number of e to the 3 halves. And don't panic if you get a weird number out of these. Sometimes that just sort of happens. So just do your sign chart. Oh, and I forgot to mention, always kind of pay attention to the domain of your function. So the domain of this, we can't plug any negatives, or we can't plug in 0 for x, because you can't do that for a natural log. So your domain is just 0 to infinity. So on your sign chart, don't have it go down to negative infinity. You're going to have it kind of start at 0. And then e to the 3 over 2. So at least it kind of narrows down your intervals to 2. So you don't have to check a lot. So just anything from 0 to e to the 3 halves, so 1. And then anything bigger than this. Now you got to keep in mind you're trying to plug in numbers that you can deal with, and you're plugging them into a natural log. So I wouldn't just randomly choose something. I would choose something that cancels the ln out. So that would be another e, and then just make sure its exponent is higher. So like e squared, because then it's just easier to deal with. Okay, so if you plug in the 1, the denominator is going to be positive, and the top, if you get negative 3 plus 0, so negative over positive is a negative. E squared, the denominator is positive, so you don't have to worry about that. And then the top, if you work it out, ln of e squared is 2. 2 times 2 is 4. 4 minus 3 is 1, so that's a positive. So our function is going to be concave up from e to the 3 halves to infinity, concave down from 0 to e to the 3 halves. And we've got an inflection point because concavity changed. So e to the 3 halves, and you're going to go back to your original function and plug this x value in and see what you end up with. So if you plug that in, you're going to get 3 over 2 all over e to the 3 halves. Well, you can't leave fractions within fractions, so you got to simplify it. So the 2 and the e actually sit next to each other. So 3 over 2e. 3/2. Okay, so there's some example problems. In the next video, we'll go over the second derivative test and what we use that for. So we'll see you then.